Namaskar, my dear friends. Let us see some problem on special matrices. So what we have done is we have seen already the theory for linear algebra special matrices in our last session. Now we'll solve some gate problems based on that. So this was asked in 2015. The problem is the value of x, this x, okay, for which all the eigenvalues of the following matrix given below are real. So the eigenvalues that has to be there must be real. So what will be the case? As you can see, this particular matrix, let us say this particular matrix is A. So it is having elements complex numbers, okay? And we have options of A, B, C, D, which is 5 plus J, 5 minus J, 1 minus 5J, 1 plus 5J. So what can you tell about this? Since the eigenvalues has to be real eigenvalues, so either it can be a symmetric matrix, you have seen already, symmetric matrix, or it will be Hermitian matrix. Now as you can see, the element of this matrix is complex, so it must be Hermitian matrix. Okay, so we'll try to solve for Hermitian matrix for this element and we'll see how to get the result. So what will happen? We know that for Hermitian matrix, my a to the power theta or a theta is equal to a. And you already know what is a theta. First you have to convert it to conjugate matrix and then you have to take a transpose, right? So can you take it? So if I take conjugate of the matrix, I have to replace all the elements by their conjugates, okay? So wherever complex number will come, you know already z is equal to a plus, let's say, jb. The z bar, that is your z conjugate, is a minus jb. That's all. So in that case, I can write it down as 10, 5 plus j is there. So I'll write it as 5 minus j. Then for rest all other elements are a real number. So I'll write it as it is. Okay. So it will become x. It will become 22, 4, 2 minus 10. And the transpose of this. Transpose of this will be what? You have to take a transpose of that. So all the row element will become column element. So it will become what? 10, 5 minus j and 4. Then it will be x 22, 4, 2 minus 10. Understood? Now our aim is we have identified a theta must be equal to a. So to get that, it must be equal to my a. And as you can see, if you compare what was my a, my a was 10, 5 plus j, 4, x 22, 4, 2 minus 10. This was my a. So as you can see, this must be equal to a. It means this x must be equal to this element, because element by element it will be matching, right? So I can tell my x will be equal to 5 plus j. Wait a moment. So my element, which is going to be this one. Yes. So my element that has to be there, as you can see, this is the x that we have to find out, and this x is going to be equal to 5 minus j. Okay. So what will happen? 5 minus j. So this is the answer. Let us take next question. Alright, the question is, which of the following statement is true for every n cross n real number matrix? Okay, so n cross n means it is a square matrix that you can understand, right? Now our aim is to see which of the following statements is true for n cross n real matrix. The options are if trace of matrix is positive, okay, like let us say we have a matrix A and trace of A is positive, okay, and determinant of matrix is negative, at least one of the eigenvalue is negative. Understood? So you know already that if determinant is negative and product of eigenvalues is equal to determinant, okay, so definitely at least one of the eigenvalue must be negative, otherwise it will never be negative value. So A is true. You can see B and C and D. If trace of matrix is positive, okay, trace of A is positive, then all its eigenvalues are positive. Not necessary. Some of the eigenvalues can be negative and very high value, and that will still make it negative. So it is not true. If the determinant of matrix is positive, then all its eigenvalues are positive. Not necessary. Let us say two eigenvalues are negative. So negative into negative will become still positive. So this is also not true. Then if the product of trace and determinant of matrix is positive, right? Trace and determinant is positive, then all its eigenvalues are positive. We don't know about it, okay? So all these three are not sure. Let us take another question. So question is, which of the following concept is correct? Which of the following concept is correct? Given as P, the eigenvalues of a symmetric matrix are real. Eigenvalues of a symmetric matrix the eigenvalue of a symmetric matrix are real. Okay, that is the first statement. Next is Q. The value of determinant of an orthogonal matrix can only be positive 1. Okay, so you know already orthogonal matrix, it can be plus minus 1, right? So this seems to be wrong. Next is the eigenvalue of A and A transpose are same. Yes, definitely. Either it is, like the matrix is A or A transpose. Both the eigenvalues will be same. So R is definitely true. And eigenvalues of symmetric matrix are real. P is also definitely true. Let's talk about S. The inverse of an n cross n matrix exists if and only if the rank is less than n. Okay. So rank is less than n, then inverse will not exist because that will become singular matrix. Okay. It means the determinant of n cross n matrix will become 0. So if determinant is 0, inverse is not able to find out, right? So S is also wrong. So you can see P and R is true. It means option A is true. Okay. Let's take another question. All right. The question is very simple. You guys can solve it. It was asked in 2016. So the question is, a real matrix A is called as skew symmetric matrix. Okay. Skew symmetric matrix. So you know already what are the option? A transpose equal to A transpose equal to A inverse, A transpose equal to minus A transpose equal to A plus A inverse. So you know already symmetric. Symmetric means A equal to A transpose, or I'll write it as like this: A transpose equal to A. And skew symmetric, this was A transpose equal to negative of A. So it's very straightforward. Option C is true. So alright guys, what we'll do next is, with this matrices is over. Next we'll start with probability. So a complete explanation of probability theory and a lot of great questions that will be that have been asked will be given in the next session. Thank you.